So we're moving on to the second set of slides for Chapter 3 and Chapter 4. Now we're going to start to talk about reactions actually taking place in solution, and we'll look at some really basic calculations in terms of stoichiometry that will apply to solutions. So now, thinking more about the way chemistry really works, especially inorganic chemistry where we're dissolving amounts in water and mixing them together. So we'll start to see some calculations that reflect the real way things are taking place a bit more in this section. So in this video, I'm just going to briefly define some terms, and we're going to go through the progression of turning a molecular equation into an ionic equation and then into a net ionic equation. So I think generally this is something you'll see apply more to the lab side of the class, but it also will help you to think about what the important components of a chemical reaction actually are, and we can kind of discard the extra information that we're not concerned with. So now we're going to be talking about stuff taking place in liquid, and so we want to define the parameters when we're considering all of this. So a solution just refers to a homogeneous mixture of two or more substances. It doesn't necessarily mean that it's a liquid, just that it's a homogeneous mixture. So in theory, we could have a solution that's actually a gas mixture or a mixture of solids. So all those would be possible to consider. Then, as we think about what's going on in our solution, there's really two types of components we can observe when we're looking at a solution. So we have the solutes, which to be a solute, it's just a component that is present in a smaller amount compared to the solvent, that's the substance present in the largest amount. So any solution is going to have one solvent, but theoretically there could be multiple solutes just depending on how many components there are in your homogeneous mixture. So down below there are just some examples of that. So something like a soda where water is the primary component and then there's other things dissolved in it like sugar, carbon dioxide, phosphoric acid, dye, if there's any color added to it, that would all qualify as a solution. But remember, like I was saying, all the qualification is that it's a homogeneous mixture. So theoretically, air is also a solution because it's a homogeneous mixture in which nitrogen is the primary component. Then we've got all sorts of minor components: oxygen, argon, methane, carbon dioxide, all sorts of things. But it's still a solution because it's a homogeneous mixture, and the major component is the solvent. And then lastly, in terms of a solid, this is a very specific example of a metal alloy. So if you've ever soldered anything, that solder wire is primarily lead with some amount of tin, neither of which is great for you to breathe. So if you're soldering a bunch of stuff, you should make sure you're not breathing the vapors that are coming off of that. But really, any metal alloy like steel or brass, technically that's a homogeneous mixture with two or more substances in it, so it also counts as a solution. All that being said, right, generally speaking, when we think about solution in chemistry, we're thinking about a solvent and things dissolved in it, and in general chemistry or inorganic chemistry, we're thinking about stuff that's dissolved in water. Down here in the bottom right corner, it's showing solutions of KMnO4. So I think MnO4 minus was not one of your to learn polyatomic ions, but that's the permanganate ion, MnO4 minus, and that permanganate ion has a pretty distinct purple color to it. So all this picture is really showing here in the bottom right corner is that we could have varying concentrations of our solute in our solvent, and that's going to totally change the behavior of that solution. So when we do get into the stoichiometry part of things, which will probably be in a couple of videos, it's going to be important to have a useful unit of concentration so we can think about how many molecules are present in our solution or how many moles are present in our solution. A distinction we want to make when we're thinking about solutes that we're adding to our solvent is considering electrolytes versus non-electrolytes. So an electrolyte is just something that, when dissolved in water, causes the solution to conduct electricity. And then on the other side of things, a non-electrolyte would be something that, when dissolved in water, produces a solution that does not conduct electricity. So in theory, if I had pure water, so just a tub of H2O molecules, in theory, that would be a solution that doesn't actually conduct electricity. It's actually the electrolytes in water that are causing the water to conduct electricity. But to genuinely get water that is electrolyte free is pretty difficult, so generally we just think that water is a good conductor, but it's a good conductor because of the electrolytes that are pretty much always in it. So these three pictures across the bottom, on the far right we see electrolyte solution, so that's what's in the beaker down below, and then there's kind of this light bulb set up with a power source, but it's got the wires dangling down into the solution. So in theory, we would need, let me change colors there, we would need electrons to be able to flow freely between the two ends of that wire in order to close the circuit. And if that is the case, then the light bulb will light up. So same thing here, we'd need the ability for electrons to travel through that gap. These two that are electrolytes, one is weak and one is strong, we'll talk about that in a little bit later, you can see the light bulb lights up to varying degrees. But on the far left, this non-electrolyte, it doesn't light up. And what that means is that we aren't getting electrons to travel from one end of the wire to the other through this solution, therefore the bulb is not lighting up. So an electrolyte is something that conducts electricity in solution, allows electricity to be conducted through a solution. How does it work? Well, the simplest explanation is that our electrolyte is made up of charged particles. So when I add, for example, sodium chloride into water, it breaks up into sodium cation and chloride anion. And so salt water is going to have these charged particles floating around in solution, and the presence of those charged particles is going to make it a good environment for electrons to travel through. So going back to that last picture, it'll make the bulb light up. And officially, a strong electrolyte is something that dissociates completely. You can see my example is the same as the one already on the slide. Something like sodium chloride, sodium nitrate, potassium nitrate. There are lots of ions that break down completely and then produce charged particles in our solution that makes it conduct. So anything that behaves this way, that it breaks down 100% in water, we call it a strong electrolyte. So many of the ionic compounds you learned to name in Chapter 2 would also qualify as strong electrolytes. On the other hand, we could also have a weak electrolyte. And that means it breaks apart, but not completely. So it generates some charged particles, but not that many. In general, with the exception of mentioning it right here, we're going to defer all weak electrolyte discussion to the second semester class, and that's something you'll talk a bunch about in the second semester if that is in your plans. But the highlights here, this is CH3COOH. That's actually the formula for acetic acid. And acetic acid is the primary component of vinegar, right? Vinegar is just acetic acid in some amount of water, and that molecule acetic acid breaks down to form the acetate anion, also not one on your list, plus some H+. So what's important here, and I think it's going to show this on the next slide as well, is this reversible arrow. So that's a clear indicator that the reaction does not go to completion. It just means some reactant gets turned into product, not all of it. And depending on the substance, it can be of varying degrees of going to completion. But nonetheless, a weak electrolyte will produce some charged particles, which will allow for some electron flow through the solution. Therefore, the bulb will light up a tiny bit, like we see here with our weak electrolyte. Okay, so like I said, it's showing that reversible arrow here. We can either say the reaction can occur in both directions, or it just doesn't go to completion. And again, this acetic acid, it's a weak electrolyte because it ionizes, breaks apart into charged particles partially, and that's what that reversible arrow is telling us. So now our primary interest is to start to think about what's going on in water, right? And so we're considering the fact that an ionic compound like sodium chloride is going to fully dissociate in water and break apart. Well, what's going on? What do we think about with regard to the water molecule that makes it possible for these ionic compounds to dissolve? Well, this is a picture of the three-dimensional structure of water, and it more or less looks like this kind of bent structure with oxygen in the middle and hydrogens off to the side. We're not there yet, but we'll get to it, not in this chapter, in a couple chapters officially, but what ends up happening in the bonds between oxygen and hydrogen is effectively there's a tug of war over electrons between the two atoms. And in each case, oxygen is going to win that tug of war. So we can indicate that with these arrows. They're really vectors with the arrow head pointing toward the atom that is winning that tug of war, and then that crossed line for plus at the side that is losing that. And so because electrons are negatively charged, the net result is the oxygen that's pulling the electrons toward itself has a partial negative charge, whereas the hydrogens that are losing the tug of war has a partial positive charge. We'll explain in more detail what's going on with all of that, but essentially elements in the upper right part of the periodic table are very good at pulling electrons toward themselves, and as we go down and to the left from there, elements get worse at pulling electrons toward themselves. So in that regard, that's why I know oxygen would win the so-called tug of war with hydrogen. So once that's all settled, it means there's a partial negative end to the water molecule and a partial positive end to the water molecule. So what ends up happening is when I have a cation, the plus charge of the cation faces toward the oxygen side of the water molecules where there's a partial negative charge. Then on the opposite side of that, if I have an anion, the anion gets to see the water molecules oriented, so they get to see the H side, the H partial positive hydrogen side of the water molecule instead. So this unique behavior of water makes it easy for water to accommodate the dissolving of an ionic compound because it can be set up with the oxygen side facing in to stabilize the cation, or it can be set up with the hydrogens pointing inward to stabilize an anion. So for that reason, it's easy for ionic compounds to dissolve in water because both the cation and anion can have favorable interactions. So then with all that in mind, right, our understanding that charged particles are what makes something an electrolyte, it's creating a solution that accommodates electron flow, then the other side of the coin should be fairly straightforward, just to say a non-electrolyte is something that, although it dissolves in water, doesn't produce charged particles. And the best examples I can think of for that are sugars, right? Lots of sugars dissolve in water, but the dissolving process of sugar happens to not involve breaking down into charged particles. It just dissolves as is. So there aren't charged particles to accommodate electrons flowing, so it's a non-electrolyte. So technically, if I took pure H2O and added sodium chloride to it, that would produce a solution that conducts. But if I took pure H2O and added sugar to it, I think this is glucose in particular, but a sugar to it, it would not conduct electricity. That light bulb would not light up. This table just shows some different classifications of which are which. Don't need to worry too much about that. The non-electrolytes are primarily molecular compounds, things that don't break down, whereas the strong electrolyte compounds are things that break down, and in fact break down completely. So you can see some of the acids you learned how to name are in there, as well as the bases, and then lots of ionic compounds that dissolve in water as well. Weak electrolytes, we don't need to worry too much about that. We gave our one example of acetic acid, but that's really as far as we need to get thinking about weak electrolytes. So now that we're in a chapter where we're thinking about solution chemistry, we want to spend a little bit of time thinking about different reaction types. So in this video, we'll introduce the precipitation reaction, and we'll use the molecular, ionic, and net ionic equation notation to consider a reaction. So precipitate just means solid. If we have a reaction where we mix two solutions together, and the result of mixing them together is the production of cloudiness of a solid, then that solid is called a precipitate, and the reaction is called a precipitation reaction. A lot of times, precipitation reactions also end up being exchange reactions, meaning that the ions switch partners during the course of the process. So that's something that we want to be able to consider. So in this reaction, we're combining together silver nitrate and potassium chloride. I'm going to just give each portion its own color. So silver, nitrate, potassium, red, I guess, chloride. So that's how things are paired up to start with, right? Silver, nitrate, and potassium chloride. And so these reactants are going to switch partners. Let's see if I can keep my color scheme the same. Probably I'm going to forget. What did I do? I think yellow, blue, purple, red. I think so. Yeah. So then, if we follow that, we can see the partners are switching. So silver goes with chloride, and potassium goes with nitrate. So that's an exchange reaction because the ions swapped partners going left to right in this reaction. But there's something else important happening in this reaction as well. AQ, 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 describing things that are dissolved in water. But here, with silver chloride, it produces a solid. So it used to be that at this stage in chemistry class, you would start to learn solubility rules, where it would essentially predict for us these compounds are not soluble in water, these compounds are soluble in water. But typically there are so many exceptions to those rules that I don't really find it useful to learn those rules. You can just look it up when you need to. But chlorides of things like silver are not soluble in water. So in the course of this double exchange reaction, we've also formed this precipitate, silver chloride. So as part of the exchange reaction, we end up with silver chloride. It says S next to it for solid to let us know now we have a precipitate. So this is an exchange reaction that's also a precipitation reaction, and we see that because we started with no solid and now we have a solid. So it's important to pay attention to these subscripts in our chemical equations just so we can try to understand what's going on, whether it's a solid being formed or a gas being formed or whatever it may be. It's important to pay attention to what this part says. Okay, so same that I just said, helpful to pay attention to exactly what species are present in a reaction mixture. And if we're going to understand reactivity, we need to pay attention to this sort of stuff just so we can figure out what's taking place during the course of the reaction. So the main thing I want to do from here is follow the process of making a molecular equation into an ionic equation and then on to a net ionic equation. So what we're doing here is really going to apply to ionic compounds and ionic compounds in which it says AQ after them. So in this case, the silver nitrate, potassium chloride, and potassium nitrate, these are things that are going to break down 100% in our solution. We know that because it says AQ after them and they're ionic compounds, but the silver chloride is going to stay put. So we're going to convert silver and nitrate into silver plus 1 and nitrate minus 1, potassium chloride into potassium plus 1 chloride minus 1, and potassium nitrate into potassium plus 1 and nitrate minus 1. This process that we're going to follow to go from molecular equation to ionic equation to net ionic equation, the purpose of doing this is it'll help us get a better understanding of what actually is taking place during the course of our reaction. So when we change the ionic equation, the molecular equation to the ionic equation, that's exactly what we're doing. So let me rewrite the molecular equation just above here. Silver nitrate aqueous plus potassium chloride aqueous makes silver chloride solid plus potassium nitrate aqueous. So now for the three aqueous components, we're going to break them up into their respective ions. So silver nitrate, potassium chloride, potassium nitrate. The silver chloride ends up staying the same because it's a solid, meaning it's not dissolving and breaking up into ions. It's staying put as a solid throughout this process. So in the ionic equation, you're likely to see redundancies, right? You're likely to see things that appear on both sides in identical ways. And these are what we refer to as the spectator ions. And when we go from the ionic equation to the net ionic equation, we're going to cancel these out. So the potassium cation shows up on both sides, nitrate anion shows up on both sides. So it was the ionic equation. When I cancel out like terms, that gets me to the net ionic equation. So once we do that, then we have the simplified version of the equation that tells us what really matters. So what really matters? Silver plus cation finds chloride minus anion. They react in a precipitation reaction to form silver chloride solid. So for a relatively wide range of reactions, following this process of changing the molecular equation to the ionic equation to the net ionic equation is a good way to kind of cut to the chase so we can actually consider what's important in our particular process. So then here we are finally with our actual net ionic equation, which says despite all the decorations, all that's going on is silver cation is finding chloride anion to form silver chloride precipitate. So to kind of recap what we did there, right, to get to the net ionic equation, you're crossing out anything that doesn't change from the left side of the equation to the right. So exactly identical. And these things that don't change at all, we refer to them as spectator ions. So potassium and nitrate were our spectator ions in this case. And the goal in doing this is that we end up with just having the only things left in the equation be the part that really matters, the stuff that's undergoing changes. So the silver and chloride ions finding each other to make silver chloride precipitate. So if we follow this process, right, we start with a molecular equation, and it's important to make sure it's balanced before we go forward. Then we dissociate all strong electrolytes, so break apart all of our ionic compounds. Anything that has an S after it's going to stay put. That'll get us to the ionic equation, right? So step 1, we're at molecular. Step 2, we're at ionic. And then steps 3 and 4, crossing out stuff that remains unchanged, and then rewrite it with the species that remain. That's how we end up with our net ionic equation, which, like I said, can be informative because it'll help us to understand what actually matters in the course of our reaction. Okay, let's take a look at one more example of this, and then I think that's a pretty good place to stop this first video for this set. Okay, in this case, here is our reaction. Lead 2 nitrate plus sodium iodide makes lead iodide solid plus 2 sodium nitrate. So you can see here's our precipitate, right? The lead 2 iodide. Everything else it says AQ, AQ, AQ. So we'll break them down. This is a little different from what we did last time because there are subscripts here and here in our formulas, so we're going to have to take those into consideration. All right, so I think I'm going to back out to a separate sheet and walk through this process rather than showing you what I already have written down. So let me do that real quick. So it was PbNO3 2 aqueous plus 2 sodium iodide aqueous makes, let me make sure I'm following it the same way, PbI2 solid plus 2 NaNO3 aqueous. So now, one by one, I can break down the aqueous ionic salt. So this becomes Pb2 plus AQ plus 2 NO3 minus AQ. And then from here, plus 2 Na plus aqueous plus 2I minus aqueous makes, and this stays the same, right? PbI2 solid and then plus, sorry, I made it a little sloppy here. Let me clean that up. Plus 2 Na plus 2 NO3 minus both aqueous. So that's the ionic equation right at this stage. And so then to get the net ionic equation, I look for what appears identically on both sides. And it looks like the sodium and the nitrate are the same on both sides, and those are our spectator ions. So then these will cancel out with each other, and that gets us just to the real details of what's happening, which really is Pb2 plus aqueous plus 2I minus aqueous makes lead 2 iodide precipitate. So that lets us really consider what matters. Despite all the other information that's around, it's really about lead 2 finding iodide minus. They react together to form a precipitate. So if you're reading through things and it talks about memorizing solubility rules, to me that's kind of a thing of the past because it's so easy for us to look that kind of information up. And if you do encounter a solubility table, it's really going to say all of these are soluble except these 5 exceptions, or all of these are insoluble except these 3 exceptions. So really, for the most part, other than some obvious ones, you end up looking up the information anyway. So I don't see a reason for you to memorize any solubility rules. Okay, let me go back to the slides, but I think that's pretty much all I was planning to say here. They go through the same process, right? Starting with the molecular equation, going to the ionic equation. Here you can see crossing out the spectator ions on each side to ultimately get to the important part, which is the net ionic equation. And then it just happens to mention here, hey, those are the spectator ions that are being canceled out when we go from ionic equation finally to the net ionic equation. Okay, in the next video, we'll talk about acids and bases a little bit. Oxidation and reduction will come up soon after that. And then we'll get to some stoichiometry calculations that fit in with solution chemistry.